with some background, some principle of TCSPC. So if we go to the first slide, why do you want to use fluorescence microscopy or fluorescence spectroscopy? Now I can only see my screen, but I don't see the presentation.
Yeah.
So Mark, can you change the screen to the presentation, please? Yep. Okay, I hope everyone can see the presentation now. So the fluorescence, why do we want to use fluorescence? Well, it's sensitive compared to absorption measurements or reflection measurements. It can be selective depending on what filters you use and what fluorophore. And of course, it's non-destructive. You can shine light on your sample, you can get some fluorescence back, and you can still keep your sample. Now, there are many ways that people have used fluorescence. I won't mention them all. I just want to say that the most modern ones. So people are using them a lot in the low-dimensional materials, including diamond vacancy centers. So in other words, you can grow your synthetic diamonds. People have also been using it in low-dimensioning nanomaterials, like 1D and 2D materials and carbon nanotubes. And in the second part of my presentation, I will give some examples of how NIR fluorescence is used in material science, life science, and we hope that it can be used in point-of-care medicine. So if you go to the next slide, you will see that I'll give a kind of an overview of the concepts of TCSPC, including the intensity, spectrum, and lifetime. Talk a bit about the Jabronski diagram, the information it can give you, how you can represent your sample. And then in that it also shows the Stokes shift, and I will go to the instrument response function, the IRF, and see how that affects, how that is important in your fluorescence measurement. And then how can we measure fluorescence lifetime? How do we use time domain measurements in time-correlated single photon counting? And I will say a few words about first resonance energy transfer, or FRET. On the next slide, again, why do you want to measure fluorescence? Because it's sensitive, selective, and non-destructive. And it can do things. If you do single photon measurements, you can do things you cannot use with analog techniques. If you know the exact arrival time of a photon, you can do a lot with information. Of course, it's the highest sensitivity because a single photon is the lowest energy level that you can detect, the lower light intensity you can detect. You cannot split a photon into two. Indirectly you can, but that's a different thing. And of course, there's high time resolution. Intrinsically, it has the potential because if the photon arrives at a certain time and you have the right instrumentation, you can know exactly when it arrives. How do we measure that? You can see on the right-hand side of the slide some of the instrumentation that we use. On the top, you can see the range of detectors, SPET detectors for visible and infrared, a superconducting nanowire detector, and on the bottom, the ID900, our electronics. Let me first go back and explain some concepts. So what is fluorescence? Well, fluorescence, when we see it with our eyes, we only see intensity. You can see based on the color, whether it's say blue-green or green, bright green or yellow-green, you can get a little bit of information about the spectrum. Those are both static measurements. But the other two out of those four parameters you cannot see. So if you look at fluorescence, it's also one of the characteristics also its lifetime. When a molecule is excited, it will take a fraction of a few nanoseconds before it emits the light. It emits its fluorescence. Another parameter which we cannot see, some animals can, is polarization. In other words, if you send light from a laser with one polarization, and it will change over time, and that time is then also in a fraction of nanoseconds or a few nanoseconds. you can look at the polarization or its decay. It's called anisotropy decay. So again, there's four characteristics: intensity, spectrum, lifetime, and polarization. On this slide, the Jabronski diagram, it kind of represents all the different events that can happen to a molecule that is excited by light. So if you're excited by laser light, you can see that the blue up arrow, it goes from the S0, the singlet, the ground state, to the S1, the singlet excited state, and then within a fraction of a few femtoseconds, it goes down to the lowest S1 state. So that's mostly just a very low heat transition. Once it's in S1 state, there are many things that could happen to this molecule in excited state. It can either fall back to the ground state and just give off its energy as heat. That is the dashed arrow that goes down. But there are also molecules, and some molecules do that much better than others. They can emit that energy as light, fluorescence. That will happen then on the order of a few nanoseconds. There are some other processes. That energy can also, from the singlet excited state, it can be transferred through intersystem crossing to the triplet excited state, and from there it can go down to the ground state, which is phosphorescence. It can also go back from a triplet excited state to the singlet excited state, and then go down, which is delayed fluorescence. Those are standard things for the molecules just by itself, but there's other things that can happen. If another molecule is nearby, and if it rocks in the same way, in other words, the dipoles match up, that other molecule can steal the energy, and that's in a process called first resonance energy transfer. So that will cause a dimming and shorting of the lifetime. I'll come back to that later. Another thing that I want to mention in this diagram very briefly is that you can see that you need a little bit more energy to excite your molecule than the light that comes out. And that shift is called the Stokes shift. So if you have a molecule in the visible at a high energy level, that Stokes shifts tend to be more energy for the same wavelength difference. Say if you have 100 nanometer wavelength difference, is that your Stokes shift that equates to a higher energy level difference than if you have an infrared. On the next diagram, you can see a very basic setup. So here you can just see a laser illuminate your sample. Your sample emits fluorescence. You detect that on a single photon detector. And then you record that with our time electronics ID900 time controller in our case. This is a very specific diagram. In an overall diagram, you also deal with a laser. Your sample can be a lot more complicated, passive optical components. Then again, you detect it and you record it. Now, each of those components will add to the instrument response function. So the overall instrument response function is an important parameter in your fluorescence measurements because it tells you about your timing uncertainty. Maybe in the next slide, I can show a little bit more about IRF. So some of the instruments, like the electronics, if you have a 20 picoseconds full width half max, full width half max timing jitter, it shows it up as a sharp peak. In most cases, on the right-hand side, the graph is a graph of a typical detector. In the visible, if silicon-based detectors, you can have about 50 picoseconds timing jitter. in infrared, it tends to be a little bit larger. So in our case, we have detectors that go down to just below 100 picoseconds. More commonly, it's like 150 picoseconds to 200 picoseconds. You can measure the instrument response function directly. Often it requires quite a bit of change to your experimental setup. So on the next slide, I show a few measurements of the overall instrument response function. On the left-hand side, if you measure them by scattering of the laser light onto gold nanoparticles towards your detector, you can see that we measure a full width half max. There's an overall instrument response function of 170 picoseconds. A much simpler way is also just using milk colloids, so colloidal milk solids, and then you also get about a similar full width half max, in this case about 190 picoseconds. So that's your overall instrument response function. That is this sum, and I think that's what I indicate on the next slide. The sum of your all the components. So you can also mathematically approximate it. The overall setup, including laser, and then your passive optical components that determine the central part of the setup, your detector and your electronics, can be approximated by taking the square root of the sum of the squares of your elements, of the components. And as I mentioned, it's an important parameter to evaluate your fluorescence capability. I'm going to give a couple of examples. The first example is that if you have electronics that have 20 picoseconds time jitter and is using a silicon detector with 50 picoseconds, you can still see that your overall IRF is dominated by the detector, because the overall IRF is 54 picoseconds. Now, what would happen if you would be able to have timing electronics which would say only have a 4 picosecond JIT? Then your overall IRF would be, say, 51. So it doesn't really make much difference because it's the detector that's your limiting factor. This is for silicon, for visible wavelengths. It's even more pronounced when you go to infrared. So in the next example, you can see again, if you have an in-gas detector and your timing jitter on the detector is 150 picoseconds, the electronics is 20 picoseconds, your overall IRF is about 152. So it's slightly more. If you would change electronics to 4 picoseconds, your overall IRF again would still be 150 picoseconds, which is completely determined by your detector. So when people ask me how do I optimize our system, then you look at what contributes mostly to your overall IRF. It's mostly the detector, and that's often the way to improve it. In most cases, when people use laser, people use a dash sapphire laser or a fiber laser with 6 picoseconds, which is what I used here in the example. If you use a pulsed diode laser, then your laser can actually be a limiting factor. This is all what I want to say about IRF. If you have questions about it, please ask. We'll be happy to say that. I want to go back to fluorescence. As I mentioned, there's quite a few different ways of looking at fluorescence. The most common one is just looking at fluorescence intensity. So if you look at different samples, and then maybe the next, so you can see there's different intensities, bright green or very dim or almost oversaturated green. It will tell you about the concentration of the molecular species that you have in your sample. If you want to know more, because often it can be a mix of species, you can look at the spectrum. So if you can see if the sample is blue-green or bright green or with yellowish green, you know you're going to be dealing with different compositions of fluorescent molecules. And if you measure that at different wavelengths, you can probably deconvolve that and know what contributes to your sample. But what we want to do is we want to know more. We want to know about the environment that it's in. We want to know how it behaves. We want to have a dynamic measurement. So if you look at fluorescence lifetime, which is on the next slide, then you can see that you often start with a very bright sample, and over time, and that time is nanoseconds, it will extinguish. The fluorescence will emit fluorescence, your sample. So you can look at the interactions, and if you look at different samples, you will have different decays, so you can get information about its interactions and its environment. On the next slide, I'm giving you a bit more information about what it means when you measure fluorescence decay. If you have a very concentrated sample and you give a laser pulse and you have the appropriate detectors to measure it, what you will see is that you'll see your fluorescence within a laser period of, say, 10 nanoseconds. The fluorescent intensity goes down from bright to non-existent. That's not what we want to do. What we want to do is we want to have a very low sample concentration, say 1/1,000,000th of it. So rather than 5 millimole, we want to have, say, 5 nanomole, which also is more realistic when you deal with biological samples. If you then excite your sample with your laser, often you won't get any photons. So in other words, you just measure, you just see a black, you don't see anything, you just see black in response to your laser pulse. But every so often, you will see a bleep, and that's indicated by this bar on the third and on the fifth diagram. And if you accumulate those, if you do that for, say, a few seconds, and if you have your laser apparates in the megahertz, it will only take you a few seconds. You can build up a histogram because you can record of all those events that you did measure a photon. You can build up a histogram. If you build up a histogram, you can see that within this 10 nanoseconds pulse period, you will have most of the photons arriving very early in that period and some very late in that period. So you get a histogram of your photon distribution. So you can get information about your fluorescence lifetime. Of course, in addition, you can also measure just the timestamps. You can measure them only timestamps, or you can measure the combination of both. I think on the next slide, I kind of given an implementation of it. So what we can see here is the small box on the right is your pulsed out laser. It can illuminate your sample. You can detect it on the very right-hand side with, in this case, I showed the ID210 and the ID220s, which are older generations single photon detectors. So, and then the third element is your electronics, the ID900 timing electronics. So in a schematic view, the way to go is that with your laser, you excite either directly or indirectly. You'll trigger a start. Now we don't have to do the start. You can also just use any input doing that. At the same time, when you do that, you excite your laser, excites your sample, your fluorophore in your pipette. And when that emits a single photon that is detected on our single photon detectors, say the ID cube or superconducting nanowire detector, it will trigger another channel, another input channel, which can be configured as the stop channel. So you have the time difference between the start and the stop, which can build up your histogram. So if you, because you pulse a laser many times. How does it look on our electronics? If you look at on the left-hand side in the red box, you can see that in here we have a laser that's being pulsed at almost 20 megahertz on input 2. You can see the frequency is about 19,000. And because we're dealing with a very dilute sample, we only get, say, 1,263 counts on our detector. So it's a fraction of less than 1% of the samples that are of the laser pulse that results in an emission. Still, that's enough information to make a nice decay graph. So on the right-hand side, you can see the decay profile. And because it is a logarithmic scale and you have a single exponential decay, it appears as a straight line. And the angle of that line tells you a bit about the fluorescence lifetime. There are many other things we can do with our time controller. You can see there are some coincidences you can measure, and you can actually look at the counts. On the next slide, I give a recap of the single photon counting. Again, you have a laser pulse, and on the horizontal lines, it will show if there is a photon being detected. In most cases, not. Every so often there is. So if you record the time in the laser period that the photon is detected, you repeat this measurement many times, a few million times, or a few hundreds of million times in a few seconds. You can build up the histogram of the time in the laser period and the frequency that it happens. So the frequency N is on the vertical side. One of the applications of TCSPC is first resonance energy transfer, or FRET. If you remember the Jabronski diagram that I showed you earlier, you give a laser pulse, the light is absorbed by a fluorophore, in this case called the donor. That light is emitted after a few nanoseconds. But if you have an acceptor molecule nearby, and there is enough spectral overlap between the emission and the detection, this acceptor can actually take this energy. And sometimes this acceptor is also a fluorophore and will emit that light further in the red, red shifted, or the acceptor can also just be a dark acceptor and emit its energy as heat. It doesn't really matter because we're not so much interested in the acceptor, we're interested only in the donor. So on the right-hand side, you can see what happens if you just have one fluorophore, no acceptor nearby. You will see the light green decay. It says no FRET and unquenched donor. So it takes a long time, long meaning many nanoseconds, for the fluorescence to quench. But if you have acceptor molecules nearby, they can quench the donor. So in other words, the area underneath the curve gives you the intensity. The slope is much steeper, so it can tell you about the distance that the acceptor is away from your fluorophore. It's very sensitive because it's the distance is scaled to the power of 6 with your energy transfer. Often what you have is you have a mixture of donors that are close to an acceptor and some that are very far away. So you end up with a fluorescent resonant energy transfer fraction, so the FRET fraction, and you will have a double exponential decay. That's actually good because that will give you an internal standard, because you have a non-interacting free FRET and an interacting FRET. On the next slide, I'm giving you another view of how FRET is. Again, FRET measures dynamic molecular interactions. If you have no FRET, you have a very slow decay. If you have fast FRET, you have a you have a very rapid decay and you have a much lower intensity. You can also see that from the left compared to the right, either the donor is a free molecule or it can form a complex with an acceptor. I think that's all that I want to say so far about the concept. If you have more questions about it, we're more than happy to address those. So please enter your questions in the chat box for that. What I want to do in the second part of my presentation is give a few examples of fluorescence lifetime in the near infrared. And it's a little bit dubious of what people mean by infrared. Often some people means from 750 to say 850 or 900. Other people means it's beyond the band gap of silicon. So we'll go say from 1100 to 1700. That's often what we define as in near infrared. Other people call this wavelength range shortwave infrared, SWIR. So the first example is an example about singlet oxygen measurement. The second one is about inorganic dyes. There are many people doing inorganic dyes. Again, I will show you the setup. We have three parts, the laser, detectors and electronics, and the setup is what most cases the users have set up on their optical table or in application, instrument application. Next slide. I'll show you the same setup that I just showed in a diagram. Just on the front top right, you can see it's just a very simple cuvette setup. I don't even have a beam splitter, just a bandpass filter. But it does the work. It does the job. The next slide is a little bit more fancy setup on a confocal microscope. So you can see that we use a laser to excite a Q-switch laser in the high energy, say in this case, depicted by green. A green bar is illuminating your sample, and when the sample molecules in the sample fluorescence goes through your dichroic mirror onto your detector. And in this guy, it's a SPAT. It's one version of SPAT is called a negative feedback avalanche detector. It will cause a stop in our electronics. A start was given by the laser pulse, and you do it many times, you build up a histogram. So in the next slide, you will show off-singlet oxygen luminous and show you the spectrum. It is a very, very weak signal. It's often barely detectable, and it's detectable at about 1200 nanometers. In most cases, people have not been able to detect it simply because most people deal with silicon detectors, and you do need in-gas detectors or other material that is sensitive to infrared to measure it. So it's a very weak luminescence, and you can improve on that by changing the setup. So if you look at the next slide, it will show you two different ways of measuring it. So the first graph on the left-hand side shows you having measured it with the setup that was depicted. You excite with a simple laser at a fixed repetition rate, and you detect your photons. On the right-hand side is a little bit more advanced method, and you can see that's a lot more cleaner measurement of luminescence. It has a very nice decay, single exponential decay. And it is done with a new method, which is called synchronized excitation detection. The advantage of that is that you actually take advantage of the dead time of your SPAT detector to excite your sample in its dead time. On the next slide, I give you another example of of fluorescence detection in the infrared. Many people are developing new dyes for the infrared, for microscopy, for cuvette measurements, because more and more people want to go into redder wavelengths, because they'll cause you less, so lower energy will cause you less damage to your sample, especially if it's a biological sample. And you can also penetrate deeper in opaque or turbid media. You can see that most infrared dyes have a very short lifetime, and so they're very difficult to distinguish sometimes from the background. So the overall IRF can be an issue. You have to carefully deconvolve it, and you may have to make sure that the measurement you've done for your instrument response function is accurate. At the same time, you can see that the detector and the electronics are not limiting in the overall IRF. It's more your sample. The next example that I want to share with you are quantum dots. It's a popular development. A lot of people are using quantum dots. Often they compose they have a core, cadmium selenide or lead sulfide, and conjugated with it are InGas or indium gallium arsenide. So you can see here on the left-hand side, you can see that there are different versions of quantum dots. And each of them has different lifetime, and the lifetimes of quantum dots, they tend to be in the hundreds of nanoseconds. Again, it depends a bit on the environment. And that can be a good thing, it can be a bad thing. The good thing is, for example, you can use them as oxygen centers, because a lot of quantum dots are very sensitive to the oxygen concentration. On the next slide, I show another example of quantum dots, use of quantum dots. Here, the quantum dots have been conjugated to antibodies. So if you look on the left-hand graph, the top line is HER2. HER2 is an antigen that relates to, it's one of the cancer antigens. So if you have an antibody called the anti-HER2, you conjugate to your quantum dots, you will have you can measure its lifetime. You can also conjugate these quantum dots, ER quantum dots, erbium doped quantum dots, to other antibodies injected in the tail of a mouse or another animal you use. And you can actually detect the tumor. And you can just illuminate the whole mouse with infrared light, detect the tumor. Yep, the next slide is another example of that, how people have used carbon nanotubes, one of the low-dimensional materials. And initially, the interest was using pure carbon nanotubes, and Bruce Weissman and Jean-Wei Lin have displayed that. And later on, they were interested because the carbon nanotubes themselves, the fluorescence is very much dependent on its length, and it's very low fluorescence, very low. It's not very useful. People have modified the carbon nanotubes. Again, that is by Jean-Wei Lin and Weissman, who's one of the groups. But you can actually functionalize it by conjugating your carbon nanotubes. And people in the laboratory of Landry, Marquita Landry is one group, who have conjugated, in this case with neurons, so that are then responsive to dopamine. Dopamine is a hormone or a ligand that binds to the hormone receptor in your brain, so it can affect your performance. You can see on the left-hand side, you can see there's a graph how the 100 micromolar of dopamine affects the fluorescence or the luminescence compared to the background, which is red. The last example that I want to share with you are how fluorescence can be used also in more of a commercial setting. In this case, people use it for checking the integrity of perovskite thin films that are used for solar cells. Again, you can see that the fluorescence lifetime is very much dependent on the sample and on the homogeneity in your sample. So you can see the black curve goes down quickly compared to the colored curves, the blue, the orange, and the red ones. And in this case, when people deal with solar cells, when they talk about infrared, near-infrared, they're talking about 720 to 820, which is still possible to measure with silicon detectors. Again, you can see this from 720 to 820 nanometers on the right-hand side. That was my last example that I want to give you. There are many more examples that how people are using single photon detection infrared. We can talk about it later, or you can ask me or send questions to info@Quantique or directly to me. Again, why do we want to do single fluorescence? Because we can do things that cannot be done with analog techniques, because we can do time domain time-correlated single photon counting. It is very sensitive, because single photons is the lowest energy, lowest photon packet you can measure. And it has intrinsically high time resolution because your fluorescence is instantaneous. You measure the instantaneous emission of a photon. And then how we do it, we combine lasers with our detectors, with our electronics, and then our users provide the passive optical setup. I want to conclude the webinar with saying, okay, so an RF instrument response function is relevant to single photon counting because it gives you a quantitative measurement of the accuracy of your measurements. I talked a bit about fluorescence lifetime, one of the characteristics of fluorescence, and one of its applications of fluorescence lifetime is time domain infrared. It's one of the methods used in TCSPC, time-correlated single photon counting. I give some examples of single oxygen fluorescence, novel near fluorophores, quantum dots, and carbon nanotubes. It comes back to the way I think of it, it's technological advances that drive science and commercial applications as much as our progress in theoretical advances. And there is a tendency for detection further in the infrared and shortwave infrared. So that's for us an impetus to develop more of the technology and the methods to apply it. So if you have questions about how fluorescence lifetime and how single photon detection can be used or can possibly be used in your investigation or application, please don't hesitate to contact us. More than happy to share our expertise in this area. With this, I want to thank you for listening to my webinar, and we should be able to answer some of your questions. Oh, a few words about quantum sensing. As I already mentioned, we combine our detectors, which are on the left-hand side, with our electronics to provide quantum sensing solutions. And there is a wide range of applications. It can be in quantum physics in the laboratory, in life sciences, material sciences, but also we're using it a lot in communication and other applications, like in OTDR, security sensing, and oil and gas. With that, I would like to thank you to listen to my webinar. And if you have any questions, please post them on the site. We'll try to address. Thank you.
Thank you, Rick. Thank you for the presentations. We do have a couple of questions.
Somebody is asking whether we are going to share the slides, and the answer is yes. You are going to receive an email with a PDF copy of the slides. Also, the webinar is going to be available as a replay on the website, so don't hesitate to go to our website for a replay of that webinar. So that's the first question. There's another question about the possibility to use the technology in a more real time. What could you, Rick, give some perspective about the timing, the acquisition time, and possibility to move on to real-time measurements?
Yes, you can do real-time measurements, of course. When you say real-time, you mean that, I presume that you mean that during the acquisition, you can actually look at the buildup of your photon counts, and yes, you can. We have, in electronics, there are counters, so you can save your the files during the acquisition. You can actually, not in the GUI, the graphical user interface, but if you use your own programs and using Skippy commands, which we provide, you can in real time measure things like the first moment. If you look at fluorescence, you can also look at your timestamps. So yes, you can.
Okay, thank you, Rick. Another question on the solar cells: is it used for quality controls already? The technique?
Yes, it is. Yes, it is. It is used to scan. If you have wafers made, you can, because the efficiency of your solar cells depends a lot on the purity of the substrate layers. They are being scanned for the impurities, and those impurities will show up as with a different fluorescence or different lifetime.
Okay, thank you. Questions on, you showed an example with a mice. Is it a technique that is used for human beings? Do you have examples?
No, it's not yet used for human beings, because we're not allowed to inject quantum dots in people yet, because of the hesitation of using materials that are very small, nanomaterials, in humans. We don't want to have a repeat of the asbestos scare.
Okay. Let's see if there are other questions. Wait a second. Right. No, there's no further questions. So once again, thank you very much for attending this webinar. Stay tuned for more webinars, which will be announced on our website. And if you are, please subscribe to our newsletter, and you will be informed about new webinars and other events that we are organizing. Thank you again, Rick, for this webinar. And please also see if you have other questions, or if you want to know more about our products, please send an email to info@idquantique.com, or you can contact directly Rick at Rick Van Gogh. So I think I've got your email. Okay, the email address is now displayed, to Rick Van Gogh at idquantique.com. So thank you very much. And with this, we are concluding this webinar.
Thank you.